General relativity is the prevailing framework of modern physics. It accurately maps the cosmos at massive scales, yet it contains a well-known mathematical flaw. At the center of extreme masses, the equations break down. This breakdown generates the first pathology of the theory, the inevitable formation of singularities. In these theoretical points, mass density and spacetime curvature reach mathematical infinity. That leads to the second pathology. The Weyl tensor, which calculates tidal forces, predicts that the gradient of gravity diverges to infinity as you approach a radius of 0. This is the origin of spaghettification, the idea that matter is infinitely stretched. Version 26 of hyperbrane relativity, or HBR, argues that these pathologies are not physical realities. They are mathematical artifacts created by forcing the universe into a 3+1 pseudo-Riemannian spacetime. To eliminate these infinities, we have to abandon the concept of spacetime entirely. We must replace it with pure spatial geometry. Solving the black hole problem requires us to stop treating time as a fundamental dimension and instead rethink the foundational shape of the universe. HBR introduces a 4+0 pure space ontology. The universe is embedded in a four-dimensional Euclidean bulk, mapping to coordinates x, y, z, and w. In this model, the observable universe is not a mathematical boundary with zero thickness. It is a three-dimensional volumetric brane with finite thickness, extending along that fourth spatial dimension, the w-axis. General relativity visualizes gravity as a bottomless spacetime well. HBR visualizes gravity as a physical, finite depression along this w-axis. Notice that time is completely removed as a coordinate axis here. Instead, HBR uses a bridge relation, dt equals dw over vw. What we perceive as time passing is actually a local emergent parameter. It tracks the physical motion and flow of energy relative to the w-axis. Converting time into a measurable spatial process introduces physical boundaries. It allows us to apply structural limits to gravitational wells that the math of general relativity cannot permit. This brane is highly dynamic. It drifts slowly through the w-axis, continuously receiving energy flowing in from the w- direction at the speed of light. To a co-moving zero-point observer living inside the brane, this slow drift is entirely undetectable. But the gate-amplified inflow of energy manifests physically as rest mass, E equals mc squared. In this model, mass is not an inherent property that pulls. It is a result of the background energy stream. This shifts the focus from what matter is to how matter interacts with that flow. This suggests a mechanism based on pressure rather than attraction. Specifically, HBR proposes that gravity is an external push caused by geometric shielding. When two masses are near each other, the first mass blocks a portion of the 4D energy inflow arriving at the second mass. It casts a shadow in the energy stream, creating asymmetric pressure that pushes the objects together. Through the geometry of 3D solid angles, this asymmetric pressure mathematically resolves into a strict 1 over r squared force. It mimics Newtonian attraction perfectly, without requiring any actual pulling force. If gravity is external pressure deforming the brane, then the structural integrity of the brane itself dictates what happens when two massive bodies get uncomfortably close. Early iterations of hyperbrane relativity relied on an assumed vortex repulsion mechanism to stop objects from collapsing at short distances. It was a patch to make the math work. Version 26 abandons that assumption. The solution was already embedded in the field equations through a property called intrinsic bending rigidity, applied directly to the brane's Lagrangian action. Denoted as kappa k squared, bending rigidity is the energy cost required to sharply fold the 3D spatial brane into the fourth dimension. It acts as an extrinsic curvature penalty. When two massive w-axis wells collide, their geometric fields immediately overlap. The local curvature between them violently spikes. The brane structurally resists this acute curvature. Bending it any further incurs a massive, rapidly compounding energy cost. The brane physically refuses to fold infinitely. This geometric resistance generates a powerful, short-range repulsive force that physically overrides gravitational collapse. This equation displays the mathematical approximation for this two-body interaction energy. The left side of the equation is the standard gravitational well, pulling the objects together. This aligns identically with established orbital mechanics. The right side, the 1 over r to the 5th term, represents the violent repulsion driven purely by the curvature cost of the brane. At macroscopic distances, this repulsive term is so small it is negligible. General relativity holds true, and planetary orbits function normally. As the radius between the bodies shrinks, the denominator of that second term vanishes so rapidly that the repulsive force explosively overtakes the gravitational push. The exact spatial boundary where repulsion equals and then exceeds gravity is the transition radius. Because this rigid repulsion actively halts gravitational collapse, the spatial metric coefficient phi remains strictly greater than 0 at all times. If the spatial metric coefficient can never equal 0, the formation of a trapped null surface, an event horizon, is mathematically and physically impossible. A single structural constraint, brane rigidity, resolves 3 mathematical crises in astrophysics. First, because matter faces a hard curvature limit, it can never form an event horizon. Second, because brane bending is physically restricted, the gradient of spatial distortion hits a finite ceiling. That restriction physically eliminates the concept of spaghettification at the center of massive bodies. Third, when 2 massive bodies undergo a close proximity binary merger, they do not collapse into a singularity, they experience violent repulsion. Black holes, defined as infinite singularities by general relativity, do not exist. They are simply exhausted fountains of dense matter, physically capped by the rigid limits of 4D spatial geometry. The mathematical structure of HBR leads to specific, observable deviations from general relativity. The 1 over r to the 5th repulsive term acts as a physical brake during the final in-spiral phase of a binary merger. This chart graphs a standard gravitational wave waveform over time. The solid line represents the template predicted by general relativity. Under HBR, the waveform shows a slightly suppressed ring-down phase at peak merger, driven by geometric braking. This specific structural deviation makes the theory directly testable using datasets from existing laser interferometers and future space-based missions like LISA. Advanced analyses of existing merger data may already contain the subtle signatures of this bending rigidity. If observational waveforms confirm the signature, it would indicate our universe is not a 4-dimensional spacetime, but a 3-dimensional volume shaped by the bulk.